All right, I guess we can start. This is one more session of the Summer of Data series. We've been doing a lot of talks on synthetic data and pre-training so far, and Syeda is one of the persons who has done incredible work during her PhD while co-working at CMU and NVIDIA, from papers on reward analysis-based pre-training to synthetic data for math and even across multimodality. She has done synthetic data work across the spectrum, and I feel like a lot of people here have frequented her works, especially when trying to iterate over new synthetic data designs. So very excited for your talk today, and hopefully we can pick some of your brain on how you think about the next generation of synthetic data as well. But yeah, I would love to see your perspective behind all of these papers that we've been reading passively.
Yeah, thank you, Pratyush, for the introduction. And I'm really happy to be here. I think I have mentioned this to Pratyush a couple of times that his work was the first one that actually was, that was basically my reference work for me that to get started on the pre-training part. But yeah, I'll just start sharing my screen. Let me know if you can see my screen. Is it visible?
Yes.
Okay, great. Let me just see that everything works well. Is it on full screen? Okay.
Yes.
Okay, great. So yeah, we can get started. So yes, hello everyone. I'm Syeda. I have recently graduated from LTI at CMU, and I will be joining NVIDIA ADLR team as a research scientist, I think late in June. My team works on building LLM, which is called Nemotron, and I specifically work on improving the reasoning ability of Nemotron models. And today I'll be presenting the summary of my works on reasoning and pre-training mostly. To be honest, this is basically my couple of slides from my thesis defense. So yeah, let's get started. So for years, we believed that scaling up more data, bigger models, and larger compute would simply keep making our models smarter. The famous chinchilla scaling law even gave us a recipe that for every doubling of model size, we should also double the number of training tokens. However, while compute keeps growing with faster GPUs, better algorithms, and even larger clusters, the data we have is not scaling. In fact, studies predict that by around 2034, we will run out of new web text to pre-train our models on. As Ilya Sutskever at NeoReefs recently said, pre-training as we know it will end. He even called data as the fossil fuel of AI. So even though we could keep building bigger and bigger models, without better alternatives to smarter data, the scaling era will eventually hit a wall. To address the scaling data problem, the field has shifted its attention towards alternative and sustainable data sources, which is called synthetic data using LLMs. Synthetic data enables scalable training beyond limited internet data. It reduces reliance on expensive human-level data and accelerates convergence as we easily can control the quality of the generated data. Now, these expansions have made our LLMs smarter, achieving near perfect accuracy on general purpose reasoning tasks that represent system 1 thinking. But when we talk about system 2 thinking, which is complex thinking ability, current LLMs are still unpredictable, stumbling across basic reasoning questions, which raises further concern. Are our LLMs learning to reason at all? So definitely, naively scaling data is not all we need, which has been widely explored in recent literature that synthetic data has diminishing returns after a certain point, causing the risk of model collapse. So all these realizations have directed us towards the question, how can we move beyond simple scaling to build models that can truly reason? To get there, we need to answer three fundamental questions. First, we need to understand what actually makes data smart, what defines the high-quality reasoning data. Second, we need to identify when to inject that data, at which phase of model development it brings the greatest benefit. And finally, we need to rethink the learning algorithm itself, ensuring that the model is not just exposed to reasoning data, but is truly capable of learning to reason from it. So when humans are faced with a problem, we don't jump straight to the answer. We explore multiple possible solutions in our heads, weighing options, testing hypotheses, and finally choosing the one that makes the most sense. LLMs, on the other hand, are trained very differently. During pre-training, they mostly learn from surface text, what humans say, not how they think. As a result, they often end up memorizing the shallow patterns instead of understanding the reasoning that led to those correct answers. But the key insight is that every piece of text actually hides a rich trail of reasoning, small trials, feedback loops, counterexamples, and these hidden structures are fundamental for teaching our models how to reason and build the foundation of smart data. In this talk, we want to define the attributes of smart data and how to construct such data to obtain generalizable reasoning gain in our LLMs. Next, let's take a step back and try to look at how human cognition develops over time. So according to Jean Piaget, there are 4 cognitive stages of development in humans. And most importantly, individual may never reach the highest stage of reasoning if they miss the opportunity to reorganize the knowledge at the right time. Moreover, researchers have found that human brain is specifically plastic during certain periods of childhood when it is more sensitive to specific environmental stimuli. For instance, language learning is far easier in early childhood, and learners who acquire a new language after puberty can rarely attain native-like grammar or pronunciation. So this leads us to the conclusion that building reasoning skill is very time-dependent, and missing the optimal windows can lead to disadvantages that are difficult or sometimes impossible to fully recover later. This brings us to the next set of research questions. Is there any plasticity in LLM development? And if so, then at which stage of LLM development integrating such smart data has a durable and non-trivial improvement? And is there any synergy of smart data across training phases? Now we have smart data and we know when to inject it. But the next question is, how do we make sure that the model is actually learning to reason, not just mimicking the patterns? In nature, supervised learning is not the fundamental learning process, yet it remains the core component of how we train our LLM today. Animals, including humans, they don't learn by being told what is the right answers. From a very early age, humans learn through trial and error. They try things, fail, adjust, and gradually figure out what works. We don't copy each other perfectly. Instead, we learn by acting, by seeing the consequences of our own choices. As Richard Sutton famously quoted, there is no basic animal learning called imitation. The scalable learning method is that you learn from experience. But in LLM, this kind of learning from experience, which we call as reinforcement learning, this comes very late, long after pre-training. So the question becomes, can we bring this idea earlier into the training pipeline and design algorithms that can enable reasoning to emerge naturally? So all these insights and limitations in our current literature can be summarized along these 3 key dimensions. And in the rest of the presentation, we'll work through each of these 3 dimensions. First, with smart data, understanding what defines the high-quality reasoning data. I will skip the training and ablation details. I mean, I won't go in depth of those details, but for the sake of time. But please let me know if you have any questions. I'm happy to share the details later. So at the beginning of the presentation, I was sharing how synthetic data provides a way to handle data scarcity. That exploration began with quite a few papers where textbooks are all you need was one of the notable ones. They released a model called Phi that was pre-trained on synthetically generated textbooks. This model led to some controversies where the model was extremely good at benchmark tasks, but it was equally bad at general reasoning tasks. By the way, I can see the screen, so if anyone is raising any questions or anything, I won't be able to see. Please let me know.
Yeah, we just raise our voice. And
Okay. Okay.
I mean, in the wrong way. You got the meaning.
So then later there was another paper from Pratyush. They also showed a way to synthesize data by rephrasing using LLM to remove the noise that we have in our raw wave text. However, that data provided good gains in general purpose reasoning benchmark. But the gains that we see in slightly complex reasoning tasks, they were minimal. So this shows that naively synthesizing data has minimal effect on complex reasoning tasks. Therefore, we need smart data that can capture the hidden reasoning behind the words. This hypothesis led us to work on Mind that transforms raw text to conversations. To begin with, why do we need Mind? Mind breaks down the raw text to step-by-step multi-turn conversations to elicit the hidden thought that we have in our raw text. Next, Mind leverages the knowledge imbalance between the participants in the conversation to further enhance the reasoning depth. And finally, this enables the continuous generation of unique synthetic data from a single document by employing infinite conversation style. So this is how Mind works. Given a prompt that represents the conversation style and raw data, which is taken from Common Crawl or other web documents, we deploy a conversation generator LLM to obtain a conversation specific to each prompt or style. So basically, in total for each text, we have 7 different conversation. Next, we do heuristic filtering to filter out the bad conversations. Finally, we combine the raw pre-training data with synthetic conversations and deploy continuous pre-training on top of the base model. This is how the Mind conversation looks like. So as you can see, unlike the raw text, which is in the blue part, the conversation is much more structured and detailed. Most importantly, it produces complementary reasoning that was never present in the raw text. As you can see, like the content that we have in the red text, they were never present in our raw text. It is basically, they're explaining why this is the reasoning behind this particular solution. We test the utility of Mind data through continuous pre-training on a 7 billion parameter model, trained till 50 billion tokens. Using OpenWave math data and 7 conversational prompts, we generate around 130 billion token of synthetic reasoning data. And for comparison, the control model uses OpenWave math and Common Crawl data, while the treatment model replaces OpenWave math data with Mind conversation. We then evaluate both of these models across general reasoning, math, and science benchmarks. First, we address the most obvious question: is the conversational data actually beneficial? As the result suggests, pre-training with conversational data yields 5 to 13% gain in math tasks and 0.8 to 4% gain in complex STEM tasks, showing the strong effectiveness of Mind data. And finally, combining all dialogues yields the best number, showing that the conversations with varied style can surpass the model trained with unique raw tokens. We also explore whether the prompt style or prompt type influence the effectiveness of Mind data. Our qualitative analysis reveals that conversations where there is an information flow between the participants tend to be longer and richer in explanation. For example, a teacher adds a lot more details and explanation while conversing with their students. To quantify this, we measured the correlation between raw text and generated conversations across different prompt style. Conversation between two professors were highly correlated with the original text, meaning that they added little new content. In contrast, layman know-all and teacher-student exchanges showed much lower correlation, reflecting deeper elaboration and reasoning diversity. This pattern carries over to the downstream task performance. Models trained on two professor dialogues perform similarly or slightly worse than the model trained on raw data, while knowledge gap-based conversations consistently yield better results. So the summary is clear. Effective reasoning data emerges when there is a gap in understanding that forces explanation, clarification, and reflection, which is the very core essence of smart synthetic data. So far, we have seen how smart data can instill generalizable reasoning ability during pre-training. The next question is, can we achieve the same effect in later stages, specifically during reinforcement learning? Since the success of DeepSeek R1, reinforcement learning with LLMs has become a major focus, particularly for math and coding tasks. These domains work well because they have clear rules and verifiable correctness criteria, making the real modeling very straightforward. But when we move to broader reasoning domains like humanities, law, or social sciences, things get tricky as they don't have the deterministic answers. Even the reasoning structure differs. For example, multiple choice questions involve comparing given the options, whereas the open-ended tasks require constructing reasoning from scratch. So these challenges motivated us to develop nemotron cross-think, a framework designed to make reinforcement learning viable for diverse reasoning tasks. Here is the overview of cross-think methodology. We start by curating data from diverse sources. Then we apply structured template to control the answer space complexity. We filter out questions with non-verifiable answers. We prepare an optimal blend that utilizes data from multiple sources effectively. And finally, we deploy reinforcement learning on top of the base models. For data, we curate open source data spanning general purpose and math domains. And we also synthesize multi-domain data from Common Crawl to further enhance the domain diversity. We emphasize on domain and question diversity to enhance the cognitive flexibility and broader generalization of LLM. So we begin the results section by addressing the most obvious question. Does combining multi-domain data actually help? As the chart shows, every blending strategy outperforms the base model by a clear margin. And among them, the more GPR blend, which uses a 2:1 ratio of general purpose to math data, achieves the highest overall average. And we refer to this blend as nemotron cross-think. Cross-think not only surpasses the base model, it also outperforms the math-only models, including OpenReasoner 0, which was trained exclusively on complex math problems, demonstrating that diverse reasoning data leads to more balanced and generalizable reasoning ability. We have also revealed a very important finding that nemotron cross-think uses 28% fewer tokens for correct responses, which leads us to the conclusion that exposure to multi-domain data enables the model to internalize an efficient reasoning strategy, leading to both improved performance and reduced inference cost. Later.
Sorry, I have a quick question. Did you explicitly try to induce output token output token length reductions in any way in this pipeline, like either just through shorter examples in the synthetic data or like anything, or through the curation, sort of some of the input curation side? I'm quite curious.
Yeah, so this is a good question. So basically, we are running reinforcement learning. So even though we create synthetically generate smaller reasoning traces, the model will probably not be able to use it, right, during training. So I think here the fewer tokens is basically when the model sees like diverse type of questions, not only just math questions, but also like general purpose reasoning questions. It sort of like now learns that for math questions, I need to reason longer versus for like easier math questions, I need to reason shorter. Or like, for example, in general science questions, I don't need to reason, for like more than like 100 or more tokens because they are easy to answer. So it's like because the model is now seeing during reinforcement learning, seeing a lot of like different type of reasoning questions. And that's why the model is also internalizing those adaptive behavior when it is getting exposed to different type of questions during evaluation. Does that answer your question?
Yes, it sounds like it is. It seems like it's probably a result of just the distribution of examples it's seeing being somewhat shorter, in part because it's not, math answers tend to be longer and it's not biased towards, entirely math data.
Yeah,
this is also particularly interesting because like certainly on the RLHF side of things, a lot of reinforcement learning ends up making models that are way more verbose, not more
exactly. That was one of the motivation of on why we were working on this problem, is that what is the optimal balance between multi-domain data that does not make the model verbose, but at the same time it also does not lose a lot on the accuracy side as well.
Thank you.
I'll continue with the presentation then.
I have one more question. One thing I've noticed is that often the domain that was responsible for a certain behavior has a very strong correlation with at inference time also. So models will pick, like if it's a math question, it will quickly map internally to its math data, and which if it was always long, it will probably still answer long. Like, did you do specifically something that merges the distribution of general web with math? Because my experience has been that models are quite bipolar in the sense that they would really rely on the distributional characteristics unless they were explicitly merged within its weights.
I'm confused. I'm not sure like whether I got the question correctly, but what I want to clarify here is that probably I missed that in the previous slide, is that how we prepared the blend is that we used a 2:1 ratio. So of general purpose to math data. So in our training distribution, so like we use twice as much general purpose reasoning questions compared to the math data. So that's one thing I wanted to just clarify. And please, you can ask your question again. Sorry.
So what is the prompt for the general purpose reasoning like? Is it also something?
Yeah, we use the same prompt. So we did not change anything apart from like whatever question we are putting inside, and all the template and all the prompt and everything is the same.
Okay, that makes sense.
Yeah, it's not like we tailored anything. And that was one of the things that we also wanted to check later, is that if we just tailor the prompt, not only just during the training time, also during the inference time, if we just tailor the prompt specific to certain task, whether it will improve the performance or not. But we didn't, we saw like there was a rapid improvement, drastic improvement in like general purpose reasoning tasks when we change the prompt to specific task. But for this work, at least we wanted to make everything consistent, and just wanted to see what is the impact of this domain distribution when we train, we run reinforcement learning.
Got it.
Okay. Yeah, and later we also checked the dynamic range in response generation for neutron crossing and only math and open resonance zero models. So neutron crossing is a multi-domain is a model trained with multi-domain data, where only math and open resonance zero were only math only models. So as shown in the graph, crossing increases the average token by 62% when generating responses for math tasks, as opposed to general reasoning tasks, whereas the dynamic range is much smaller for only math and open resonance zero models, which is 12 and 14%, 14 and 20% respectively. So this adaptive behavior highlights a key strength of multi-domain training, is that it equips the model with the flexibility to tailor its response style to the nature of the task, producing compact yet accurate answers where appropriate and a detailed one when necessary. Now, looking at the current trend, every new day we have new LLMs coming up. We distilled data from those stronger teacher models and we feed them to a weaker LLM and expect that it has mastered reasoning somehow. But do we know the core component of this high quality data? Summarizing the qualitative exploration in this topic, we found that longer reasoning traces have multiple hypotheses to solve a problem, and they also have a reflection and refine stage to retrospect on the solution. So we narrow down the key ingredients into 4 types, which is question, hypothesis, answer, reflection, and refine. Now, if we just build data by leveraging all these ingredients repeatedly, will we attain the true reasoning? Unfortunately, this is not as straightforward as it looks. As we know that these models sometimes become very verbose and to solve even a simple calculation. For example, to choose a number, DeepSeek R1 took 96 seconds of thinking. We don't know what it was thinking. So these insights motivate 3 research questions that we want to address. What is the impact of each ingredient on reasoning? Does scaling some ingredient or increasing reasoning depth provide any improvement? And can we emphasize one ingredient over the other one while scaling this data? To study this, we construct the data from scratch using Numina Math as our seed corpus, which already has chain of thought solutions in it. For each question, we first generate an answer. Then we prompt the model to reflect and refine using the ground truth chain of thought. We then push this further by introducing a hypothesis phase. So the model first plans how to solve the problem and then produces the answer. And finally, we move beyond a single reasoning path by enabling multiple hypotheses and creating loop between hypothesis generation and answer refinement phase. We run continuous pre-training on a 8 billion parameter model for 50 billion tokens, first with our raw chain of thought data, then with our synthetic chain long thought data that we have just generated. To combine the ingredients, we try 2 setups. So here the case 1 is the setup number first, which is without tags, where the units are combined without specific markers. And the second case is with explicit tags for each reasoning step. So here we use the question, solution, or reflection refinement as our specific tags when we are pre-training the model. As shown, without tags, the long thought data that we have just curated brings little gain over the raw data. As you can see, like the bars are basically negative. However, when we pre-train with tags, we see visible gains over raw data, specifically when we do multiple hypothesis solutions, reflections, and refinements. Next, we build 2 blends.
A small question here.
Yeah, sure.
Sorry to interrupt. Did you see any distributional shift in the previous answer and the reflect and refine answer? Was it like the model was answering incorrectly and then in reflection it was correct? Or was it like the answer itself was correct and the model reflected that, okay, I did a good job?
Yeah, that's a good question. We did not do that sort of ablation or anything. I mean, It's like how many times the reflection is getting correct or not. But I will share some of the ablations just after 2 slides probably, which might share like much insight is that how the reasoning is actually getting developed inside the model. But yeah, we didn't do specific that part of analysis where we see like how the reflection is actually helping or something like that.
Okay, thank you.
Also, I have a question. Like, I see on the screen that is CPT on 8B700B LLM. Is it like a 8B model pre-trained from scratch for 700 billion tokens? Okay.
Yeah, and then we continuously pre-trained for another 50 billion tokens.
Okay, thank you.
Okay.
And does the pre-training mix have math?
Yeah, it has seen all sorts of data. Like I mean, yeah, not all sorts of data. Like I mean, whatever should be the
General mix.
yeah, general pre-training corpus. Yeah.
When you say tags, does that mean you add special tokens or just like tags?
Yeah, special tokens like the questions, reflections, refinements. Yeah. Okay. Where was it? Okay. So yeah, next we build 2 different blends. One is Numina math heavy, and the another mix is long thought heavy mix. So basically we mixed each of these blend with general pre-training mix, but here we use more Numina math data in our blend versus in the another blend we use long thought data more, which is also in 2:1 ratio. And we pre-train and compare this model with a model pre-trained with general pre-training corpora under the same token horizon. And during evaluation, we first evaluate with general few-shot examples. Then we modify the few-shot answers to align the answers with R1 style reasoning, which has a lot more reflections and refinements. Just to explicitly emphasize on this part is that we did not change the question, we just change the answer. And we found that evaluation setup is as critical as the data itself. Long thought data shows minimal gain over the baseline when few shot examples lack reasoning steps. However, when the few shot examples are rewritten to include thinking and verifying patterns, we see a 4.6% absolute improvement on hard math tasks. To summarize the long thought experiments, we find that simply generating longer reasoning traces is not enough. Structure and evaluation alignment are critical to see real gains. Now, let's step back and ask what actually changes inside the model when we introduce such structure reasoning data. Starting with mind, the behavioral shift is much clearer. The model uses 14% more tokens when producing the correct answers. This suggests that it is allocating more computation to reasoning rather than jumping straight to the answers. More importantly, 85% of the correct solutions include step-by-step reasoning and refinement process. So the model is not just thinking longer, it is systematically verifying and improving the answers. And finally, we see a shift in how the model reasons. When we combine all mind conversational styles together, the model learns to choose the right reasoning style for the question dynamically. So the easy questions get solved primarily through layman know-all style, which is simple and direct explanation. But the harder questions are dominated by debate and problem-solving style, which is the model the model is actually essentially arguing with itself to reach the correct answer. Now let's connect everything. Why do these high-quality data help? How these approaches translate into measurable behaviors and actual performance gains? In this setup, we combine both mind and long-thought data during pre-training. So on the bottom left, we conduct a probing experiment and ask, can the model recognize when a particular reasoning step is wrong? As shown, the model pre-trained with high-quality data, high-quality long-thought data shows a much stronger rethink signal compared to the baseline, So the model is not just copying patterns, it has internalized when to correct itself. The radar chart highlights the behavioral difference between the models. Nemotron, which has seen both mined and long-thought data during pre-training, shows much broader use of phrases like verify, re-examine, reconsider. This means the model has learned a richer self-correction strategies, not just a single reasoning pattern. And this internal awareness directly translates into model performance. Nemotron consistently outperforms others with largest gains on hard reasoning tasks like AIME and math level 5, where the correction and verification matters the most. So the story is consistent. Reasoning is encoded internally through high quality reasoning data expressed behaviorally and validated by benchmark gains. To summarize what sorry.
I had one question, like how much is this dependent on the few shot example, like all of this, like these results? Because I think 2 slides ago you said that the few shot examples do seed how the model actually responds. So
that's a good question.
Are there, right?
Yeah, so here, the last slide, what I presented, here we did not use any elaborated few shot examples. So we used the standard few shots that we use for all of the models. I mean, I think most of the models that they release, they use the same set of few shot examples. So we did not even change the answer. So we kept everything consistent. So I think the difference between the long thought versus the very last slide is that in the last slide, we combined both long thought and the mind data. So, but we still see like a larger improvement compared to the other models. But yeah, the slides that I was showing with only with the long thought data experiments, there we just use the long thought data, which is only just for Numina math, a very controlled experiment.
Good, thank you.
Yeah.
Also, one more quick question: like, what models were we using for the long thought and cross thing?
So the cross thing is a Quen model. So we did not do any. So we just took the Quen based model and we ran RL on top of the Quen model for cross thing. But for long thought, we used a 7 billion parameter model, which is a like transformer model. And
I meant for the synthetic data.
Oh, sorry. Okay. For synthetic data. Okay. For long thought, we used Quen 3 32B model. Was it Quen 3? Oh, okay. No, I think like Quen 2.5 32B model. And for cross thing, there were a couple of different models, to be honest, because we were collecting data from different domains. So I think for math, we used DeepSeek or something like that. And for the general purpose reasoning data, we used probably Quen 2.5 models mostly. I mean, those details are in the paper. Sorry, I don't have like those specific details like which model we use for which different tasks. Because like we used multiple models. We were not just collecting answers, we are also generating questions. So we used mostly DeepSeek and Quen 2 and 3 models to generate the data.
Good, thank you.
Yeah. So to summarize what we have learned about the anatomy of high quality data so far, both in pre-training and in post-training, is that the data must have a structured reasoning flow, capturing the logical sequence of thought. Second, it should include conversational dynamics that reflect the human-like inner monologue. Third, it needs this cognitive diversity, representing multiple ways of thinking or solving a problem. And fourth, the data should demonstrate generalization power, enabling transfer across domains and tasks. And the data should be efficient and scalable to help accelerate learning. And finally, it should possess self-expanding potential to ensure that the data can continuously grow and generate new useful reasoning examples on its own. I'll see like, okay, I don't have much time, but yeah. So then the next part is efficient integration. At which phase of LLM development smart reasoning data has the most impact? So let's look at how reasoning is typically developed in today's large language models. We start by pre-training the model on massive web crawl data. This gives the model strong language understanding and factual recall, but not real reasoning ability. And then during supervised fine-tuning, the model simply mimics the reasoning like answers without truly understanding the underlying logic. And finally, reinforcement learning helps it interact with the environment and refine responses. But by that stage, it is polishing something that was never structurally sound to begin with. It's like building a tall house on a weak foundation where pre-training forms the shaky base and post-training just adds decorative floors on top. Our core argument is that reasoning must be built or taught early. By front-loading reasoning data into the pre-training, we can build a stable cognitive foundation that the post-training can just further amplify and refine, resulting in models that just doesn't sound reasonable, but truly learn to reason from the ground up. This brings us to the central question: when should reasoning be introduced? If we include reasoning too early, could it cause overfitting or harm generalization? Or could it build stronger cognitive foundations? So the literature that we have currently is divided. Some claims that heavy SFT harms RL by reducing the entropy, and while others say it helps with the right setup. To summarize the recent works on pre-training, they show that improvement in reasoning by mid-training already pre-trained model and on domain-specific high-quality datasets and deploying RL directly on top of the base model. However, there is no phase-aware understanding of how reasoning emerges during training. There is no unified framework connecting the data quality, diversity, and the training phase. And there is no causal evidence that early reasoning creates long-term compounding benefit. Therefore, our work, front-loading reasoning, fills this gap by systematically injecting reasoning data into different training phases, pre-training, SFT, and RL, and measures how and when this synthetic reasoning data matters the most. Here is how front-loading reasoning works. We start with a base model and progressively introduce reasoning data of varying diversity, quality, and quantity across two phases, pre-training and SFT. We plug in the same RL recipe across models exposed to varying amounts of reasoning data in the previous two stages. We then evaluate how each configuration impacts the downstream reasoning performance across domains like math, science, and code. So to summarize, this design allows us to directly isolate the phase effect of reasoning data. For this, we used a 8 billion dense hybrid transformer model trained on over 1 trillion tokens. We first created a baseline model, MBase, which was pre-trained on general pre-training corpus without any reasoning data. Next, we trained our experimental models, which we call as MRes. These were trained on same general corpus, but we front-loaded the data by replacing 20% of the general pre-training data with our reasoning-focused data. For reasoning data, we define 3 categories of data: high-quality small sets, large diverse sets, and large mixed quality set. We then took all these pre-trained models and put them through the same SFT and RL by varying the reasoning data to observe the synergy of reasoning data across phases.
Can you go back? You said that 20% of data was swapped, but 6.2 trillion, like, would you be repeating a lot? Because 20% of 6.2 trillion is a lot, right?
Sorry, you mean like inside the reasoning data, the number of tokens that we have? Is
Yes,
that what
so I'm guessing 1.2 million is like 1 million
yeah.
tokens, and
Yeah,
20%
we will be. Yeah, that's correct. We'll be repeating a lot for the smaller data sets.
I see, and it's uniformly mixed, right? Right from the beginning in 20%.
Yeah, exactly. Okay. So we first try to answer the basic question, whether the inclusion of reasoning data is beneficial during pre-training is beneficial or not. So as you can see, models exposed to reasoning data early during pre-training outperformed the no reason baseline by an average of 16% across all benchmarks. Here, the reason-based model is the average of the performance of 3 models trained with 3 different variations of reasoning data. So this is not just like a single model, it's basically an average of 3 models. This confirms that reasoning is not just an alignment skill, it can and should be learned during pre-training. Sorry, I don't know why. Okay. The next question we ask is that, does the scale and diversity of the reasoning data matter during pre-training? For this analysis, we compare the models pre-trained with 3 different type of reasoning data. For SHQ, it is the high quality data where 70% of this data is about math. And in contrast, the LDQ is a diverse set of large amount of high quality data. And LMQ is the concatenation of SHQ and LDQ. So as you can see from the graph, increasing the diversity of the reasoning data, which is increasing from SHQ to LDQ, it gives a 16% relative gain across tasks, which signifies the importance of diverse reasoning data during pre-training. Now, prior works have found that exposure to large amount of high quality data in SFT can cause deterioration in RL because following up, because like they say, if we show a lot of reasoning data during SFT, the model gets very overconfident. So the RL sort of starts with very high entropy. So following up on this finding, we ask that whether this is true for pre-training, very low entropy. So following up on this finding is that we ask whether this is true for pre-training and SFT synergy. So as shown is in this chart is that models pre-trained with reasoning data not only generalize well, but also improve further during later stages, showing a relative 33% average gain after post-training, which is after SFT. So early reasoning does not make the model rigid at all. It is actually making them robust. Now, there is a very interesting finding is that we had a pre-training run where we added high quality data to our diverse mix, which is basically this LMQ data, which consists of both LDQ and SHQ. And at the end of the pre-training, the model looked about the same as the diverse only model, which is basically, as you can see, like the dark green one is very similar to the lighter one. So interestingly, high quality reasoning data during pre-training may show little immediate gain, but after SFT, it unlocks an additional 4% absolute boost. This reveals that good reasoning data creates a latent potential that is only realized later during alignment stages.
I have
Is there a question about the SFT compute?
no.
What SFT, could you just remind us what SFT compute you used?
Sorry, can you repeat that again?
What SFT compute or like SFT training bundle you used here?
Do you mean like SFT compute that I used? Sorry.
Yeah.
You're asking how many tokens?
How many tokens?
Oh, okay. So for SFT, we used 1.2 million samples. I mean, whatever data we use, we only train on 1.2 million samples. Does that make sense?
What if you extend the SFT just like by 10x, for example? Will the result still hold?
Yeah, that's a good question, and I think there is a result of that as well that I'll share later. Probably, yeah. So you mean like if we increase the SFT compute more? Yeah, actually, exactly, we did that particular experiment. I'll just share. So Yeah, I mean, before sharing that, I'll just like cover a couple of the other ablations that we have. As we have already outlined, that pre-training benefits most from broad diversity and scale. However, our next research question was how this statement holds for SFT. So here we deploy SFT on the reason-based models using 3 different reasoning datasets that we defined before. As you can see that fine-tuning on small high-quality reasoning data produces a 15% improvement over large mixed quality ones. So this is a very interesting finding, is that this emphasizes this asymmetric strategy, is that we need to build the foundation with diversity, but we need to sharpen it with quality. So in SFT, the diversity is actually harmful. And finally, the most important question, whether the I probably don't have the slide here. So what we did in one of the slides that we, one of the results that we had in our paper as well, is that we tried to increase the SFT compute by 4x. And we then tried to compare it with both like the current setup and also what if we just use that 4x compute during pre-training, what happens? So what we found is that in SFT, even if we use 4x more compute, it cannot surpass the model that uses like 1x compute during SFT, but it has seen a lot of reasoning data during pre-training. So, I mean, yeah, you cannot actually simply use the pre-training compute to SFT. Because it is still worse than the model that has seen a lot of data during reasoning data during pre-training. Does that answer your question?
So just to make sure I understand it, in the fairness setup you use which one? So let's assume there is reasoning budget we assign during pre-training, and then SFT. In the SFT there is reasoning data also, right? So there is a pre-training reasoning bucket, post-training reasoning bucket.
Yeah.
I think in the first initial setup, the pre-training reasoning bucket was much higher than the SFT reasoning bucket, right?
Yes. This is the first, for example, this is the first experiment. Yeah.
Yes. If they are, then there is a second question of what if they are equal, so the same budget here and here, and then there is a third scenario where the SFT reasoning bucket is much larger than the pre-training reasoning bucket.
Safety reasoning bucket is large. Okay. So I think the equal one is let me see, like whether we had the equal. No, we didn't have that experiment. So like there, you are mentioning about 3 experiments. So like we did not have the middle one, which is like we use this equal number of computing pre-training. I mean, equal number of samples or probably tokens in pre-training and in SFT. So we didn't have that experiment, but we had the first one and third one, where we used majority, for example, 80% of the tokens in pre-training, 20% in SFT. And then we also flipped that 20% in pre-training, then 80% in SFT. Then we also tried to do one thing, is that we used 20% in the pre-training, but we also used, we tried to do twice as much of the number of samples during SFT training. So in all of these cases, the first one, which has seen 80% of the reasoning data during pre-training, was the winner. So it was always better that having more data, reasoning data during pre-training. Does that make sense?
Yeah, when you flip it and you have 80% of the reasoning tokens in the SFT, is front-loading reasoning still better than not doing it?
Yes.
Okay.
Front loading was still better. Yeah.
Yeah. Okay. Thank you.
Okay. Yeah, I think I did not add this slide here, but in our paper we have these like clear experiments where we controlled. We did a very controlled experiment where we are just trying to see like where we should use the compute, whether it should be added during pre-training or during SFT. So
all this is under a fixed compute, right?
Yeah, exactly.
For example,
I mean, yeah, we didn't try.
SFT like to 100 billion tokens of SFT.
Yeah.
Or like 20 billion tokens of SFT. It is still under the same SFT bucket, right?
Exactly. I mean, we try to do that like under a same token horizon. Everything was same.
Thank you very much.
Yeah, no worries. I'll just probably end with this slide. So this is like what we wanted to see, like what happens when we try to do RL on top of these reasoning-based models. And as shown in the result is that even after heavy RL training, the reasoning pre-trained model maintains a 19% average lead on the hardest math, like math tasks like AIME. That gap grows to 39%. So this shows that early reasoning is not on it does not only help but also continues to pay off across all the later stages. Yeah, I think I'm also very end of the time period, but yeah, I had one more work to share, but like it's fine, I guess.
Saket,
Yeah, I have a question. I was wondering, there was this interesting McIntyre paper that came out last year by Neil Nanda, where I think it was called Base Models Know How to Reason and Thinking Models Learn When. And basically it found that like base models already have the capacity to like do thinking, but then like the RLVR stage, it basically just teaches them to almost like schedule their reasoning, I guess. And they use some different like McIntyre techniques to find that out. And they were actually able to achieve up to 90% of the gains of like RLVR just through like McIntyre steering. So I'm just curious, like whether your findings, like I guess, corroborate that. Like, do you also agree that like reasoning in the RLVR stage is more about just like teaching the model like when to reason rather than like giving them the capabilities? I'm just kind of curious how your work kind of interfaces with those findings.
Yeah, this is very good question and also an important question. So I think so one of the papers that we had was RLP, and yeah, I didn't have time to share that, but like in that paper, what we were trying to do is that integrating RL during pre-training, and the prerequisite for that was the reasoning model. The base model needs to have a lot of reasoning data during pre-training. We tried base models that, I mean, yeah, for example, in the front-loading paper that we were showing that we have a model that has only seen like common crawl and like general purpose reasoning data that doesn't have any reasoning, I mean, synthetically generated reasoning data in the pre-training. And we were not able to do RL on top of the base model at all. And we were only able to deploy RL on top of the base model and was able to get meaningful improvement when we added a lot of reasoning data into the pre-trained model. So we actually did run RLP experiments both on Quen models, and we also tried on Llama model, and we also tried on Nemotron model. So Nemotron model is basically we used a lot of reasoning data during pre-training, and we know the model, so it was really good. But Quen was also good, but Quen we were not able to get better number with like Quen 2 model or even Llama models. So they were actually garbage. So RLP didn't work on those type of base models where they were not exposed to a lot of reasoning data during pre-training. So it is very crucial to have reasoning data during pre-training to get like a meaningful number during RL.
Thanks.
All right. I guess you can all thank Syeda for her time.
Thank you. Yeah, and
Yeah,
thank you all for inviting me. Yeah, I mean, I'm missing